Hello and welcome to week 1 of Vibrations with Applications. We're going to talk about undamped free vibrations. This is the right place to start. If I can figure out where my mouse is. There you go. Here's a cute picture of some vibrations and it's from a shaft alignment book. I just thought it was funny. Here's some vibrations that we look at: pendulums and musical instruments, including guitar strings or lute strings, I guess. All right, so we'll start out with just some basic things, some standard stuff. Won't do this right here. We'll talk. You could look at that on. We'll talk a little bit about it. I guess the only thing you really care about probably is that we're going to have 3 exams, and these constitute 45% of your grade. So that's kind of important. So that'll be 15% each. We'll have, they say weekly quizzes, but I don't think it'll actually be every week. But we could just say that it's going to be every week, and then be happy when it's not. So that's going to be like 25% of your grade, and then math is hard, but we could figure out that the final exam is going to be 30% of your grade. Let's see. I'm going to follow Dr. Bob Sommer's policy, and one of the 3 exam grades can be replaced by the average of the weekly quizzes. One of the 3 exams. All right. I'm sure there'll be a whole lot of lawyering about which ones and so forth. And I think one of the weekly quizzes gets dropped. We could talk about that some more, but that's the policy. Okay. So what is vibration? Mechanical vibration. We could do a whole bunch of different definitions. So we'll just throw some up there. Some of these things you already know. So I would say repeated motion is a vibration, right? I might say shaking, sort of a shaking sensation going on. A good word is oscillations. Let's see if I spell it right. Oscillations, probably spelled kind of close. And so somebody might say moving back and forth. Moving back and forth. Another word that might come to mind: periodic motion. Right, so it repeats itself. It doesn't have to be, because we could have something like earthquakes, which is really sort of like an example, but I guess there's some examples, earthquakes. So those aren't necessarily that back and forth kind of motion. It's kind of like really a random type of thing. And I also included acoustics. So there's definitely acoustical engineering majors in our midst and in the class. So that's like a really important thing. So vibration is the lead into doing that topic. So why do we care about mechanical vibrations? Well, for the first thing, we want to reduce things like noise. Right. So I worked on ships and did some consulting. I don't know how many different trips I did specifically for vibration, but some for vibration, where we do vibration measurements and try to identify the natural frequencies that were being excited and what the excitation was. And it was almost always the propeller, but it could also be the main engine. And a lot of times the whole reason for it was because there was noise taking place, like in the crew mess or the officer mess, and it was really disturbing to people. So noise is a big concern when it comes to vibration. If you've been to any of the classrooms where maybe there was an issue with some vibration, you can see it was very distracting, and so it is a pretty important thing. But it also can cause things to fail. So that's probably, the noise is usually what people care about the most. We're trying to get rid of it. You can just turn up the radio in your car if you have too much vibration. But you can also cause failure, and in different parts, especially we'll see in ME350, if you happen to take that as a mechanical engineer, you'll see there's often going to be a fatigue type of thing. But also, if you land on the magical natural frequency of a part, the excitation from some source can hit and go in sync with a part and cause excessive motion that can make the thing fail a lot quicker. So that's That's definitely one of those instances where you can actually cause the part or the thing or whatever it happened to be working on to fail. We can also just be annoying, right? So it could be annoying motion. So in addition to the annoying noise, there could be annoying motion. There might be a reason why we would care about studying vibrations. We can also go through the acoustics portion of this and notice that we have musical instruments and they depend on vibration to get the air moving, which propagates sound. So it's definitely something that we would care about for vibrations instruments. And then in addition to that, we could have speakers, the design of speakers from an amplifier or a stereo. We also would care about vibration with the reflection of sounds. So that could be like an auditorium design. Auditorium design. These are all things that we would care about, or even just any kind of room, or any kind of room. Oops, my eraser, right? My eraser works on that pen. Any kind of room. I don't know if I need to be taking this time to do this, but I am anyway. So it's also, by the way, vibrations is also important because it's the first step in learning about or in understanding control systems. And this is and other dynamics applications. So we took dynamics. Most of you took dynamics last spring, and this vibrations is a continuation of that, and then continuing on from vibrations is to do control systems. And I didn't write systems very well, but that's all right. I'm not going to keep this systems. And these are very, very, very important control systems as a modern engineer to be able to learn this. All right, so let's talk a little bit about the different vibrations that we'll start out with. All right, so introduction to vibrations, we always start out with a single degree of freedom thing. Most often we do a spring and a mass. Single degree of freedom means there's only one coordinate that matters. In this case, this is the coordinate that matters. That is the coordinate that is free to move. Therefore, a degree of freedom, a single degree of freedom. And you'll notice right away we have an equation right underneath this. This is the equation of motion. And usually, when we have some type of model, like these are all models, a real life piece is actually more complicated than these models. But we reduce the complexity of the thing in the real world down to this simple model where we just have a stiffness of the spring and a mass of the end of the mass of the thing, and we generate this equation of motion. And then we imply, whatever words, differential equations to solve, we'll say solve this. And the solution to that, spoiler alert, is almost always, well, in this case, it is always a sine wave, right? And we'll talk about that in the next video because this is already 8 minutes, 45 seconds. But I'll continue on with my single degree of freedom. Here's another example where now our degree of freedom is the rotation. Okay, so this is some type of shaft. It has torsional stiffness and it resists rotation. And then this is a disc on here and it has mass moment of inertia, J. We often call this I. Back in in dynamics, we usually have mass moment inertia here, but here's the mass moment inertia. They decided to use J, and here's the equation of motion that you would get from employing this. And this is a different type of K, right? So it's a twisting spring as opposed to a translating spring that you had over here. Like here's the translating spring, but here's the twisting the night away spring. And then here's a very common single degree of freedom right here is the pendulum. And this degree of freedom is right there. It can go back and forth. And that you can think of a degree of freedom of the coordinate as being the single coordinate that's necessary to define what the location of the piece, right? So that single degree of freedom in this case is theta. And then this is the equation of motion. In fact, I will point out that later on, or you should note that later on, that this is actually missing a sign. And the reason is because it's too difficult of a differential equation to solve if we include the sign. So we will make a simplifying assumption to have only small angles in our solution. So there you go. There's a 10-minute video. I will try to keep most of the videos down to about that level. I'm recording a lot of these just for my own benefit so that I can time out how long these lectures will take. They're also here in case you miss a class or want to review. See you in the next section.